What is a frame-dependent displacement, and what does it have to do with the speed of light? Our map is not the terrain. Our model is not the system. Our representation is not the reality. Aside from the idea of velocity space, the most difficult conceptual distinction that I have introduced in the supervelocity and selection theory of light is that between a frame-dependent displacement and a true distance. In the simplest terms, a frame-dependent displacement is a feature of our model only, while a true distance is a feature of reality itself. Unfortunately, we cannot visualize either a true distance or a frame-dependent displacement through the lens of velocity space, because what we might want to call positional or spatial information is not represented in velocity space. Having said that, the concept of velocity space is still central to distinguishing between a true distance and a frame-dependent displacement, because the key difference between a true distance and a frame-dependent displacement is that the length of a true distance doesn't depend on where we place the zero coordinates in velocity space, whereas the length of a frame-dependent displacement does depend on where we place the zero coordinates in velocity space. Therefore, the frame-dependent displacement is relative in a way that a true distance is not, and a frame-dependent displacement is also arbitrary in a way that a true distance is not. Furthermore, if we consider a frame-dependent displacement to be dependent on the location of an observer in velocity space, then it also becomes subjective in a way that a true distance is not. Because the location of the zero coordinates in velocity space is arbitrary, then so is the length of the frame-dependent displacement. Meanwhile, the length of a true distance is a real property of nature that doesn't depend on how we choose to describe or represent it. In the glossary at page 215 of But Where is the Rainbow? Exploring the Supervelocity and Selection Theory of Light, I have defined a frame-dependent displacement as follows. The total length of the path taken by a vessel as it travels between object A and object B, where we must also consider the distance traveled by object A and by object B relative to an arbitrary inertial frame of reference during the time that the vessel is in transit. Einstein's concept of the length of the path taken by the light as it bounces between the mirrors of a light clock is an example of a frame-dependent displacement. By vessel, I just mean any discrete object that travels from some point of departure to some destination. Perhaps it would be convenient if I had a way to represent frame-dependent displacement and true distance as distinct concepts with mathematical notation. But I think that we should be cautious about searching for the answers in mathematics. Humor me while I follow this tangent a little bit further because I feel like this is an important point. I have uncovered a large number of very basic conceptual errors which have been firmly planted within theoretical physics. Interestingly, I have also discovered that most of these errors are really just the same error repeated over and over again in different contexts. I think that the errors that I have identified could be reduced if every physicist could just repeat the following mantra on a regular basis. Our map is not the terrain, our model is not the system, our representation is not the reality. Confusion between models of systems and the systems themselves have profound effects on how probability, entropy, determinism, causality, chaos, time, randomness, information, decision-making, infinity, subjectivity, locality, Planck units, and even mathematics itself are understood by physicists. As you may have guessed, this pervasive error creates a plethora of misunderstandings and conceptual knots which are difficult to straighten out. I prefer to cut the Gordian knot whenever I can, but this is not always possible. As far as I'm aware, there is no formal or recognized way to represent this particular type of error in mathematical notation. And there is also not much point in representing this error in mathematical notation. Furthermore, it's very easy to commit this error without realizing that you are doing so, and it is equally easy to just deny that any such error has been committed. To make my point about this error more concrete, I'll just give you one example. I say that probability is fundamentally abstract, dynamic, and subjective. It is pretty easy to demonstrate these three aspects of probability, especially when you bear in mind that probability is ultimately a measure of what is known. The trouble is that people have a tendency to fall into the habit of understanding probability as if it were something concrete, static, and objective. If you act as though you understand probability as something that is concrete, static, and objective, then what you are essentially doing is you are expecting the terrain to resemble the map. Probability is strictly a feature of our model of reality. Probability is not really a feature of the reality itself. I repeat, our map is not the terrain, our model is not the system, our representation is not the reality. In order to use a map effectively, one needs to use their imagination in order to pretend that one is really looking at the terrain. The real question then is, how do we implement a reality check and set limits on our imagination such that we know when and how to avoid confusing the map with the terrain? Mathematics is no different from any other tool that humans use. We can use it, we can abuse it, and we can become overly dependent on it. In physics, mathematics has been very helpful in the past, but more recently, a heavy reliance on mathematics has actually become the source of most of the persistent problems. With our use of mathematics, it's easy to see that there has been a diminishing return. We just cannot math our way out of the same problems that we have mathed our way into. I'm going to be using a fair bit of math in this video, but nothing too fancy. I will also be careful to use math as a supplement for thinking and not as a substitute for thinking. The distinction between a frame-dependent displacement and a true distance is important to understand because this is yet another way in which the map is often confused with the terrain. This incredibly subtle error leads to a cascade of confusion with respect to our basic concepts of time, space, and the speed of light. In the book, But Where is the Rainbow?, I use the example of taking a trip to the moon to illustrate the difference between a frame-dependent displacement and a true distance. In that example, the distance between the Earth and the moon is a true distance, but the distance of the trip itself is a frame-dependent displacement. I'm going to switch over to a frisbee example for this video. Let's imagine that two runners are running on a grassy field at 3 meters per second towards the north. These two runners also maintain a constant distance of 10 meters apart from one another. While running, runner A passes a frisbee to runner B. This frisbee takes 2.5 seconds to travel from runner A to runner B. Let's also imagine that there's a brisk wind blowing at 10 meters per second in the southward direction against the runners. Now we are in possession of all of the objective facts that we need. However, if we also want to say anything about how fast the frisbee moved, or about how far the frisbee traveled during those 2.5 seconds, then we're going to need to choose some arbitrary inertial frame of reference. In other words, we need to decide where to place the zero coordinates in velocity space, and we can place these zero coordinates anywhere that we want to. The location that we choose for these zero coordinates will have no effect on the reality, because these zero coordinates are merely a property of our model. The zero coordinates only affect how we describe the reality. In other words, the frisbee doesn't really have a speed, and the path taken by the frisbee doesn't really have a length. It's only when we form the false impression that our choice of inertial frame of reference is not arbitrary that we can come to believe that the frisbee really does have a speed and that it really does travel a certain distance as it moves from A to B. All that I am doing right now is adhering to the first postulate of special relativity, which is itself merely a restatement of Galilean relativity. There is absolutely nothing controversial about what I have said so far, even though it is very difficult to recall and to apply this understanding of motion in a consistent manner. So how should we position our velocity space coordinate system, which we can place anywhere we like? Let's begin by placing the zero coordinates where the two runners are in velocity space. Now the two runners are to be regarded as stationary. In that case, the frisbee covered a distance of 10 meters in 2.5 seconds, which means that the frisbee traveled at 4 meters per second relative to the runners. Now let's place the origin for our velocity space coordinate system at where the grassy field is located in velocity space, such that the grassy field is now to be regarded as stationary. In this case, the frisbee would have covered a distance of 12.5 meters in 2.5 seconds, which means that the frisbee traveled 5 meters per second relative to the grassy field. Now let's place the zero coordinates at where the wind is in velocity space, such that the air is stationary. In this case, the frisbee would have covered a distance of 34 meters in 2.5 seconds, which means that the frisbee traveled at roughly 13.6 meters per second relative to the wind. We could also place the origin for our coordinate system at the location where the frisbee is in velocity space, such that the frisbee is regarded as stationary. In this case, the frisbee would have traveled at 0 meters per second, and it would have covered a total distance of 0 meters in 2.5 seconds. Just by changing the location of the zero coordinates in velocity space, we have obtained a distance of 10 meters, a distance of 12.5 meters, a distance of 34 meters, and also a distance of 0 meters, for the total length of the path taken by the frisbee. What these four different distances all represent is the distance traveled by the frisbee in 2.5 seconds as it travels from runner A to runner B. Because there are an infinite number of potential locations in velocity space that we could choose for the zero coordinates, then there are also an infinite number of frame-dependent displacements that we could calculate for the length of the path taken by the frisbee. In this frisbee example, the distance between the runners is 10 meters, and this is a true distance. But the other distances, of which there are infinitely many, are all frame-dependent displacements. Just as the velocity of the frisbee is relative, so is the total distance that it travels in those 2.5 seconds. There is no principled way to choose one frame-dependent displacement over the alternatives. Every frame-dependent displacement is equally valid, and every frame-dependent displacement is equally invalid at the same time. But now let's say that the frisbee takes 10 seconds instead of 2.5 seconds to travel between the two runners. This will have the effect of changing the location of the frisbee in velocity space. However, in addition to that, this change in the time elapsed will also alter the degree to which the velocity of the frisbee is dependent on the inertial frame of reference. The observed velocity will now be more variable, depending on the inertial frame of reference. So now that the frisbee takes 10 seconds to travel between the runners, our 4 frame-dependent displacements would now be 10 meters, 18 meters, 65.8 meters, and 0 meters, respectively. As you can see, the range of the speeds has become relatively spread out compared to how it was before. One way to understand this mathematically is to think about a frame-dependent displacement as a velocity time, meaning that you calculate the frame-dependent displacement by multiplying a velocity by a time interval. Velocity is merely a distance between 2 points in velocity space, and therefore it is relative. But because a velocity is relative, then a frame-dependent displacement must also be relative. Because a time interval is used to calculate a frame-dependent displacement, then longer time intervals create larger and more spread out frame-dependent displacements. All else being equal, a longer time interval means a longer frame-dependent component of the total displacement. Now let's imagine that we have a time interval of 1 hour, which is pretty slow for a frisbee. If we make the time interval 1 hour long, then our 4 frame-dependent displacements would be 10 meters, 10,800 meters, 46,800 meters, and 0 meters, respectively. If we make the time interval 0, then our frame-dependent displacements would now be 10 meters, 10 meters, 10 meters, and 10 meters, respectively. In other words, if the time interval is 0, then the speed is infinite and the frame-dependent displacement is always equal to the true distance. I should also mention that the case where we consider the frisbee to be stationary is a special case because we are multiplying 0 by infinity, but we don't really need to resolve this abstract pseudo-problem in order to grasp the overall pattern. Now I want to turn to the speed of light and why it is that we need to understand this distinction between true distance and frame-dependent displacement in order to understand the speed of light. Because the observed speed of light is so fast that it is effectively infinite, then the frame-dependent displacement of a photon is also practically indistinguishable from the true distance between its point of departure and its point of arrival. In other words, the extreme speed of light makes it much easier to conflate the true distance with the frame-dependent displacement. For the most part, we can easily get away with treating these two quantities as if they were interchangeable. But treating these two quantities as interchangeable also creates confusion. It is widely believed that the speed of light is constant, meaning that it is the same in all inertial frames of reference. This is the same as saying that the true distance is equal to the frame-dependent displacement of a photon. This is not actually what the second postulate of special relativity says, however. According to the second postulate of Einstein's special theory of relativity, the speed of light is always observed to be, or measured to be, the same speed in all inertial frames of reference. It is very important to preserve this appearance versus reality distinction. We are only talking about how something appears. We have not yet drawn any conclusions about what the speed of light really is. To say what the speed of light really is would be a bridge too far at this point, and we would end up sabotaging all of our efforts to make sense out of the speed of light by jumping to conclusions too quickly. We don't yet know what the speed of light really is. We only know what the speed of light appears to be from one contradictory and incompatible perspective at a time. When considering the dynamics of light, we are drawing a qualitative distinction between an invariant speed and a variable speed. The variable speed is our original concept of speed, which always depends on the inertial frame of reference. The invariant speed is our new concept of speed that the study of light has inspired. According to the supervelocity and selection theory of light, we must not be mixing together these two qualitatively different concepts of speed. In fact, this new type of speed is not really a speed at all, and so we should not be calling it a speed in the first place. These two different types of speed are so radically different that we really shouldn't be using the same word to describe both of them. So to recap, there is both a quantitative and a qualitative distinction to be made here. The quantitative distinction has to do with the extremely high relative speeds that light achieves, and the qualitative distinction has to do with the invariance of the measured speed of light. According to special relativity, this qualitative distinction is actually a quantitative distinction deep down. In other words, a low speed is fully variable depending on the frame of reference, while a high speed is constant and an intermediate speed would be moderately variable. Many people have managed to convince themselves that this explanation makes sense, because it does, but only if you don't think about it any further. What we can be sure about is that there is a qualitative distinction here between a relative speed that depends on the inertial frame of reference and a relative speed that is the same in all inertial frames of reference. Let's call these two types of speed matter-like and light-like respectively. Along with fixed and variable speeds comes fixed and variable distances. So a true distance is fixed while a frame-dependent displacement is variable. But when it comes to the speed of light, we say that the frame-dependent displacement of light is also fixed. And what makes the frame-dependent displacement of light special is that it acts exactly like a true distance. And this is a source of much confusion. This is the equation that lies at the heart of special relativity. It is fundamental to both the light clock thought experiment and the rigid rod thought experiment. This equation is also the basis for the Lorentz equations for time dilation and length contraction, and by extension, this is also the basis for Minkowski spacetime. But there is a really big problem with this equation. There is no denying that the length of the path taken by the light is a frame-dependent displacement. To put it plainly, the length of the path taken by the light is pure fiction. There is no such thing as the length of the path taken by the light. There could not possibly be any such thing as the length of the path taken by the light. Special relativity is entirely based on taking a frame-dependent displacement and treating it as if it were a true distance. The reason that Einstein made time flexible and relative in his theory has to do with an effort to accommodate the strange invariant behavior of light's frame-dependent displacement. In order for the observed velocity of light to remain constant, Einstein assumed that the time interval must expand along with an increase in the frame-dependent displacement of light. But this cannot possibly be true, because the arbitrary location that we select for the zero coordinates in velocity space must not have any effect on the corresponding reality. The universe must not respond to the arbitrary inertial frame of reference that we choose. The supervelocity and selection theory of light provides a much more plausible explanation for the appearance of a constant speed of light. The speed of light itself is not actually constant. Rather, the speed of light is part of its velocity, which is actually spread out in a superposition across velocity space. One can think about this with an analogy of a stencil. The spray paint is spread out everywhere, but only some of the spray paint interacts with the wall. The pattern that we end up seeing resembles the shape of the stencil as opposed to the shape of the spray paint itself. We don't actually see all of the spray paint, we only see the spray paint that interacted with the wall. And when we talk about the shape of the stencil, we are not really talking about the shape of the spray paint. That would be a bridge too far. The stencil, in this case, is the spherical light bubble in velocity space, which has a radius of the speed of light, and which is always centered around the observer. The paint is the light, which is actually spread out everywhere in velocity space.